Let me start this presentation on the Xen hypervisor and our safety certification efforts. Brief introduction, I think you all know Xen is an open source project under the Linux Foundation, very well known and widely used in the industry. One thing that makes us unique is that we have a very, very strong security process and also code review process, which are some of the base foundations for our ability to making Xen safety certifiable. But another thing that makes Xen unique is that it's a true community project. We have community members from all sorts of companies, software and hardware companies. There is, as you can see, the pie chart of contribution. There is quite a variety of companies contributing, and I'm happy to say that AMD grew to be the second contributor to Xen in the last release. Both AMD x86 and ARM are fully supported. RISC-V is also under development by a number of companies interested in it, many of them interested in embedded and automotive as well. We have maintainers from all over the place. We have maintainers from AMD, of course, but also from ARM, Citrix, SUSE, Amazon, and more. But I also want to tell you of the progress that we're making with the automotive communities. So Honda joined Xen project in December 2025. That was definitely a major milestone for the project. I believe 24. Haha. Well spotted. Yes, well spotted. And we are working closely with automotive-grade Linux on a reference architecture together. And today I want to announce that Ford Motor Company joined Xen project as a member.
And Ford is now launching into an open source policy, and we've got the lawyers to agree, and so this is our first project we're at. And so, MC, if you have any questions.
Welcome. Okay, so I'm going to give a brief introduction, and the goal of the introduction, most of this information you already know, but is to make easier to understand the safety concept that I'm going to talk about in the second part of the talk. So Xen runs entirely and only in hypervisor mode, which is on ARM, using ARM terminology, is EL2. And has control over the key hardware blocks, such as the timer, the interrupt controller, the MMU, the IO MMU, the PCI root complex, and the CPU. But that is it. So Xen doesn't do anything with your devices, such as your GPU or Ethernet controller, NVMe, SATA, and all of those are just directly assigned to the guest. And the default is DOM0 here, so it gets most devices assigned by default for convenience, but you can simply take them out one by one and assign it to other VMs. So you can decide, it's very flexible in the way you can decide which devices belong to which. And then you can also run your driver, but also the backend, the virtual backend or PV backend in here and share the devices with other VMs. And we're going to talk a lot about that. But it doesn't have to be DOM0. You can also assign a device to another VM and share it from here. So it's completely flexible in the way where you put the device, where you put your sharing mechanism. The architecture is very much aligned between ARM, RISC-V, and x86. So as you can see, it's very similar. x86 had more legacy because it was the first architecture in Xen and had more variety and more legacy code. But in recent years, also, my team was directly involved into making it more lightweight, better, modern, and more similar and aligned with ARM and RISC-V. So now they're actually pretty similar, all three. So another thing that is interesting about Xen is one of the few, maybe the only hypervisor in open source that I'm aware that can do all the way from the simplest configuration, static partitioning, and real time on the right, all the way to the more complex configuration like infotainment on the left. Now, when I say simple and complex, I mean in terms of hypervisor configuration. So I used as an example the Vision Hub that if anyone here has worked on camera processing and vision is a very complicated system. But it's simple for Xen because what Xen does typically in this system is just split it into 2 or split it into 4 and guarantees real-time isolation, and that's it. So the Xen configuration is very, very simple. So Xen can go all the way from here, all the way to the opposite sides of the spectrum, where you have a lot of device sharing, like GPU being shared, audio being shared, input being shared, like touchscreen, and more. And it's up to you how you fit in this spectrum, and you can decide your configuration depending on your customer need. So another thing that is interesting about Xen is, for us, we have both ARM processors and also x86 processors. And we are using the ARM processor here in this example for the Vision Hub, the x86 on the left for IVI, connected over PCI. And we have Xen running on both. And Xen is used as an abstraction layer in terms of configuration. We have the same configuration language on both. But even more impressive, this is new, we have the first demo at Embedded World in March this year. We are able to have VirtIO connection, both local, all across the PCI link to the other cluster. So one VM running on x86, it doesn't need to know if it's connecting to VirtIO net local or VirtIO net across PCI as the other side. And it's completely mirrored. So it could be that you're doing ARM, then x86, or x86, then ARM. And it works both ways. So if you're interested about this, I don't have more on this presentation, which I'm mostly focusing on safety. So if you're interested in this specific VirtIO technology, let me know, and I can tell you more about it. OK, let me start from the right side of the spectrum, the simplest of the two, so the static partitioning. So the first thing that Xen offers is the ability to disable the scheduler. If you disable the scheduler, you have a one-to-one static assignment of virtual CPU to physical CPU. No scheduling, nothing. So this is really the configuration that you want in real-time systems. What Xen can even do is can use the no scheduling policy on some physical cores and a normal scheduling on some other physical cores, thanks to a configuration option called CPU pools. But in the simplest case, you're just going to have no scheduling, and that's pretty much it. So that's how I will configure the right side of the spectrum, where you want latency in the realm of 2 or 3 microseconds, guaranteed to be 2 or 3 microseconds, then this is the way to go. The other thing that Xen can do is can boot your virtual machine in parallel from boot. So we used to call this feature DOM zeroless. It's very confusing because in reality you can still have a DOM zero. So maybe a better way to describe it is predefined VMs. So before the system even starts, you define all of the VM that you want. You get the bootloader to load the kernels. Then the bootloader starts, and Xen starts all of the VM in parallel. But the fact that you have this feature, aside from speeding up the boot time significantly, so now, for instance, let's say that this is an RTOS, you could have very easily less than a second boot time because this path is very quick, right? But in addition to this, it also means that DOM zero here is more like optional. You don't need anymore a high privilege environment with superpowers because, in reality, all of the VMs are there. They do what they need to do, so you have it if you want it. So another feature that we have that is interesting for the people of you that are interested in real time, we have a feature called cache coloring that allows you to partition the cache line in software to prevent cache interference. So the way this works is a very clever trick to allocate memory for VMs using patterns so that the cache line they end up falling in each VM are always separate from each other. So you always end up having cache line different for each VM memory accesses, simply by the way we allocated the memory to VM. These, again, are ways in which we guarantee hard real time, right? So I really like this picture. I show it many times, and this is because I like it. But if you see here, right, we have a Xen without interference, OK? And bare metal without interference. Then you start adding interference, and this is the interrupt latency. Then you add more interference. This is the interrupt latency. Even more interference. This is internet, and look at the outliers all the way here. This is just because of the cache. Now, enable cache coloring. This is the interference with cache coloring. Add more interference. This is the interference with cache coloring. Add even more interference. This is the interference with cache coloring, right? So we have been doing real-time with Zen for a long time now, and this was one of my first projects that I worked on at Xilinx at the time, and has been very successful in production. Okay, so to summarize, our static partitioning configuration means that we can define everything statically, a number of VMs, number of vCPUs, amount of memory, device assignment, all of this is static. You can disable the scheduling to have even better real time. DOM0 now is optional, you can take it out. The footprint, I mean, the goal is then to be transparent, invisible. You don't even need to know it's there. So it boots, sets up the system, and disappears, right? The IOMMU is optional, so on ARM we can even map memory one-to-one, so all guest physical addresses are equal to physical. You don't even need to have an IOMMU. We have cache coloring for real time, and if you're not convinced that Xen is now an embedded hypervisor, we can run on systems that don't have an MMU at all. Like the Cortex R52 and R82 are MMU-less systems, so no page tables, and we can run there as well. Okay, so this is for the extreme simple static partitioning side of the story. Let's go to the opposite end. A pretty complex, sophisticated IVI system with 4 VMs. We have Android running as a guest. We have an RTOS. We have Ubuntu. We have a Yocto Linux cluster. But look at the number of device sharing in here. So we have Virtio Net, Virtio Block, Virtio GPU, Virtio TE, GPIO, I2C, input, and we even have a XenPV audio front-end and back-end. So all of these devices are virtual devices and are being shared between VMs. All right, now I'm going to start talking about our safety certification efforts. Let me premise that at AMD we have a team to improve Xen for embedded and automotive. We support customers and we deploy in production and help on multiple verticals from industrial, automotive, and others. And now we are making Xen safety certifiable. I've been discussing this for a few years. We are definitely toward the end of the project. We are safety certifying Xen IEC 61508 Steel 3 and ISO 26262 ASIL D as in Delta, which is the strictest for automotive, for both ARM and AMD x86 platforms. And what I really want to highlight is that we are now working on a private fork. All our Xen changes are upstream. Many of them are already fully upstream. Some of them are in progress right now on the list being reviewed. So our goal is that the code of Xen, the one under safety certification and the upstream code is one and the same, right? And the configuration might be different, of course. You might want to disable a certain feature for safety, but other than that, the code should be the same. And we also aim to do more than that and upstream and work with the community on certain other artifacts, such as requirements, to make sure that the safety certification it will be easy to update in the future. So it's easy to do a one-off. Easy. It's hard enough to do a one-off certification. It has already been done in the past. There was a presentation that I remember. It was in a North American Xen Summit about 10 years ago by an engineer working in the railway industry in the United States. He wanted the presentation not to be recorded, so there is no reference anywhere publicly. But he presented that they safety certify Xen for the US railway industry. So it's not like it cannot be done. The difficulty is done it with the community. And this is what we are doing now today for the first time, is work closely with the community and have this as a community effort. Okay, so the safety certification project is based in 2 phases. Phase 1, we work on what is called the safety concept, which is something that all of you that worked on safety probably already know very well. Safety concept is when you present all of your plans, ideas, how you're going to achieve safety, and also examples of basically all the major activities, all the major artifacts. And the second phase is the final assessment. So I'm happy to share with you that we successfully completed the phase 1, the concept approval. So we managed to get from the safety assessor reviews and approval signed approval that our safety plans are solid, and if we just execute on the plans, we achieve safety. Now, this is a very major achievement because it also de-risks the project, right? Everyone can say something can be safety certified, but now we can really say it, right? Because third-party assessors went through everything that we had, and together with us, we have a plan for completion. So now it's just execution, and this is what we're focusing today. Well, this was just a summary of some of the activities that we're doing for the people that don't know about safety. I'm going to leave it here for reference in the slide deck. Maybe I can give you a bit of a flavor of the activities. So one is MISRA C. MISRA C is a safe C coding guidelines. So that is basically completed. So we made Zen MISRA C compliant. We're 99% through the upstreaming. I think I have like 4 or 5 patches left total that I need to upstream. Requirements mean documenting every behavior of the hypervisor. We're making good progress there. Validation is testing these requirements, making sure that the hypervisor does actually what we say it does. Verification is a bunch of activities about monitoring the stack utilization, memory allocations, if any, time spent in Zen to make sure that the locking is correct, and we have activities on all of these. Failure mode analysis, you inject a failure and you are ensuring that the hypervisor is behaving as it's supposed to behave in terms of failure handling. And coverage 100%. Now, when people don't know about safety, if anything, to try to make it real for them, I tell them, well, we need to get to 100% code coverage, which means we need to have every single line of code tested. This is beyond that because we need to achieve even MCDC that is more than line coverage. So it means thousands and thousands of tests. Okay, so what I want to tell you today is a bit about the safety concept in terms of feature in scope and also the architecture that we enable. So first, the first point here is that we are going to split DOM 0 into 2. So DOM 0 was too powerful, right? And we don't need DOM 0 anymore anyway because we can create the VMs in parallel. So the first point, the first action here is to transform DOM 0 really in the hardware domain. In the sense that now it's not privilege anymore. By privilege, this is a word that I know means different things to different people. So think of it of superpowers, really. The power of affect others, okay? Is not going to have them anymore. So now the hardware domain is a normal VM, and the only thing that is particular about the hardware domain is that it has all the drivers by default. So all devices that are assigned to the hardware domain by default, and you can still assign devices to other VMs if you want to. We could take this away. So we discussed this. The reason to keep the hardware domain is just because it's really convenient. So if you have to manually specify all the devices where to go, the configuration becomes very cumbersome. It's very hard to have a nice out-of-the-box experience. The out-of-the-box experience is it doesn't work. With the hardware domain, you get an extremely easy and still safe out-of-the-box experience. So that's the role of the hardware domain, getting the devices by default. It can run the backend. I'm going to tell you more about the backend. What about the privilege part of DOM 0? So now, if you want to, but it's optional, you can still have a higher privilege environment, which we call the control domain. What can the control domain do? At a minimum, it can monitor the other VMs and decide to reboot the platform when needed. This is a pretty important role, right? Check when system is not behaving well, and if it is not, call a platform-wide reboot. It can do also other privilege operation depending on the configuration, but this might be sufficient in most cases. Okay, so what I want to highlight here is, yes, the control domain is going to be high privilege, meaning most likely, if you have it, it's going to be a safety certified, maybe RTOS like Zephyr, right? But it's not going to be the only one. So Xen support any number of safe VMs. Like, you don't have to have only one. You can have 2, you can have 4, you can have as many as you like of any level. They can be B, they can be D. It's up to you, right? Xen doesn't really have an opinion. It's just going to ensure isolation between the VMs, and is up to you to configure it so that your VMs don't access things that otherwise would cause interference. But totally you could have, for instance, safe Linux here as a safe VM. You could have a Zephyr side by side, both of them safe, neither of them safe, one of them safe, up to you. The other part is, like I said earlier, it's still possible to assign devices to other VM and run backends in them. So you don't have to put all of your devices in the hardware domain, right? Okay, this is a summary of the features in scope. Now, this is where the initial introduction will come useful. I hope that you can picture them. But basically, most of the things that I discussed earlier in the intro are here in the scope. So we have no OS hypervisor dependency, so you can run any OS on Xen, and also any number of safe VMs. So it could be one, can be many. The drivers in Xen are going to be very few, so only the UART, IOMMU, interrupt controller, timer. That's pretty much it. Everything is typically assigned to VMs. The configuration is fully static in terms of number of VMs, amount of memory, number of virtual CPUs, device assignment. You'll be able to reboot QM VMs. Like, one classic use case, you might want to run Android. You cannot assume Android does not crash ever. So if Android crashes, you might want to reboot Android only, not the old platform. And that is in scope. Device assignment, both PCI and non-PCI. The ability to remove the scheduler so that you have best real time. This hardware domain, control domain separation is part of the scope. VM to VM communication. And the remaining, really, slides are all about that. Because for the one of you that worked on safety before, you know that having VM to VM talk to each other is always a problem in terms of safety, especially when the VMs are of mixed criticality, meaning some of them are safe and some of them are not safe. And this communication can be a vehicle for interference. So you need to be extremely careful in how to lay out your communication or virtual device sharing. So this is the reason why, as a starting point, I always start by talking about the simpler VM to VM communication, because these are the ones that are easier to make safe, to ensure that are free from interference. So there is nothing simpler than static share memory and event channel. So static share memory and event channel is just a share buffer, pre-configured, with a way to send each other notification. That is it. Then it will be your responsibility to roll your own protocol, which will guarantee freedom from interference. And there are decades of paper written on this topic, right? So you can pick your favorite techniques to put your indexes on a different page from the ring and have, one writer, write only, the reader, read only, you knock yourself out. Pick your favorite library, right? And guarantee your safety by hand, right? Grant table, so in addition to static share memory, we can also have voluntary share memory. So you can say, I'm domain A, I want to share this page to domain B. It is only allowed because I explicitly say, I want to share this memory to domain B. Domain B can only map it because domain A granted access, which is why they're called grants, right? Because it's granting access. The last technique is Argo. So this was written by people that really, really, really care about security. And they were aware of these potential attacks over shared memory from a security rather than safety point of view. So they introduced a hypervisor-based memory copy technique. So one VM say, please then copy this buffer for me to this other VM. So VM1 never talks directly to VM B, ever. So it's always mediated by Xen on purpose because the security guys did not trust a direct communication. I do think this is very good for safety too. Many of the same principles apply, and I think this could be a viable option for your mixed criticality scenario. So all of the above, I do think are possible between safe and unsafe VMs, right? So you could roll your own little communication protocol between your safety-certified Zephyr or safety-certified Linux or other OS and your, I don't know, Android, as an example. But I know many of you are already thinking, but I really want to run Virtio. And that's where it gets very complicated very quickly. So first of all, as a Xen engineer, I could be a bit narrow-minded and say, sure, do it. Why? Because the part to enable Virtio and PV driver also needed in the hypervisor itself is truly minimal. It is so small, in fact, that definitely will be part of our safety scope. So you're going to get the ability to run Virtio frontend and backend or Xen PV frontend and backend with Xen with whatever VM that you like. So from me, as a hypervisor guy, I'll say, sure, it's done. In reality, though, if you look at the big picture, it's very far from being done, because if you look at the existing front-end and back-end, most of them don't guarantee or don't protect themselves against against interference. There is a shared ring that might not follow the best practices of separated indexes from data. So when you look at the big picture of the protocols, there are many gaps, but they're not in Xen. They are in between the VMs. So Xen is fine. It's your VMs that are not. So one simple point of view here, or one simple mental model is just use Virtio or PV driver between your unsafe VMs. So if you have an unsafe, or like, for instance, a regular Linux and an Android, knock yourself out. Use anything that you like in the default config, and nothing will impact your safe VMs on the side, right? Those are fine, right? That's one way. But what if you wanted to have Virtio and PV driver between a safe and an unsafe? So it's a problem. I can go much into details. There are many problems. I decided to focus on the two biggest problems. Let me focus on Virtio, given that that's the one that is mostly sought after in automotive. And the main two problems is, in today's Virtio, the Virtio backend, which is the proxy, really, the one that is mediating access to the device, the Virtio backend is expected to be able to map and access any memory of the frontend VM, any and all. The second problem is there are certain operations that the frontend does, the Virtio frontend, that cause the Virtio frontend domain vCPU. The vCPU is the thing that's running the frontend to completely block and hang until the backend does something. So in this case, to put it bluntly, the backend, in order to cause interference, doesn't even have to do anything at all, right? Just standing there is sufficient. So we have been working on two ways. First of all, we are collaborating with Linaro and Google and others to come up with a new version of the Virtio spec to be better than what it is today in terms of safety. There was a talk, I think, yesterday by Bill Mills on this topic, and we are very much involved with that effort. But in addition, we are also working on two tiny extensions to the regular today's Virtio that will solve both of these problems. So one tiny extension is what we call Virtio with grants. So you remember these grants over here, the voluntary memory sharing. We made it work. When I say we, I have to say I'm not going to take any credit. It wasn't AMD here. It was a member of the community that has a brilliant idea of getting grants to work with Virtio. And that alone resolved the memory privilege, like the thing of being able to map every memory of the front end. That goes away. So if you use Virtio together with grants, your backend doesn't need to have the superpower of mapping memory anymore. The second problem is the second extension here, the blocking operation. We added two simple tiny PCI registers that allow the front end optionally, to do non-blocking reads and writes. You know, it's a minimal change. I think the change to Linux to enable this is like less than 10 lines of code, but alone that would guarantee that at least the two biggest problems are resolved. Now, am I here standing saying you can use VirtIO between safe and unsafe VM? I would definitely recommend to have a deep look at those rings and protocols, making sure there is no other gaps. But at least I want to let you know that we are aware of the issue and trying to make it better. OK, so I think the last 5 minutes before the questions, I would want to give you a quick update. So where we are. So we are upstreaming key features like DOM zeroless on ARM is already upstream. It was actually made available on RISC-V just recently. And we are making the code common with x86, which had a different implementation called hyperlaunch. So we're in the progress of doing that. The hardware domain, control domain separation is on the list right now on XenDevel under review. MISRA-C, this is basically completed. We have the MISRA-C scanner from Bagsang integrated in our GitLab CI loop upstream already. 99% of the changes are upstream, and we're down to the last odd and ends commits. We are starting to work with the other interested members of the FUSA Special Interest Group on assumption of use and software safety requirement and the architecture specification. We have a few of them upstream. The requirements are the description of Xen behavior. Assumption of use are the description of what Xen is expecting from the system, from the firmware or the hardware in order to be able to run. And the architecture specification is the description of the inside, the interfaces and inner workings of the hypervisor. And I wanted to have one call out on GitLab because it's becoming more and more important for all of our activities. We have a fully open GitLab CI fully open in the sense that not only all the code is upstream, but it's even possible for anyone to trigger pipeline, any developer. But in addition, you can even contribute your own GitLab runners. So what I mean by that is, first of all, we're using GitLab to trigger tests. And the tests are of 3 kinds: analysis, build, and test. So the analysis is MISRA. The build is you build Xen on a variety of distro like Red Hat, Debian, Ubuntu, Yocto, and others. The test is you run the Xen binary either in an emulation environment, QEMU, or you run the Xen binary on a real target. So for the real target is a clever trick where the actual GitLab runner is on a controller, like a workstation, and is sending via TFTP or other method the binaries to a board connected to it with cables, literally physical cables. So we have 11 AMD hosted runners in San Jose. Where is that? AMD, here you go. Is upstairs in my office, and I manually connected many of them. But we also have many other members of the communities that are contributor runners, like Ford has contributed one runner, and CubeOS, which is a project for secure laptops to device sensitive from non-sensitive information on laptops, is also contributing quite a lot of runners based on laptops. So you have a hardware you care about, any hardware, it could be any vendor, just contribute a runner, and then automatically all the Xen tests will be run. The test will be running on this runner, and you'll ensure that Xen will keep working on that hardware. And while I mentioned this is for safety, we are relying heavily on GitLab CI for a lot of safety activity, not just MISRA. The validation tests are being worked on using GitLab integration test. The memory analysis is a GitLab job, and so on. OK, so this is my last slide, and I'm ready to take question in a second, but just as a summary, so we're working closely with the community to make Zen safety certifiable for ISO 26262 ASIL D. The safety certification is based on community processes in the community code base, and more than that, we're even working with the community on upstreaming certain safety artifacts such as requirements. There are many people that join our bi-weekly calls, not just AMD, but also Resiltech, Renesas, EPAN, Ford, Boeing, ARM, Baksang, and others. Our architecture for safety is meant to be as flexible as possible. Zen's trying to be not opinionated and let the customer do whatever they like with the system. We support any OS, whether it's safe or non-safe, any number of safe environments, and our job is just to ensure isolation between them. And definitely I want to highlight the momentum in automotive with Honda and Ford joining in the last 6 months, and the collaboration with AGL. I think Zen is doing quite well in automotive at the moment. All right, any questions? Thank you. Okay, you go first.
So thank you for your great talk. It's so much insightful. And I have one question regarding control domain view. So I guess it's very important to statically assign one physical CPU to control domain regarding real-time. But on the other hand, it could be kind of overkill for its work. So
Yeah.
my assumption is correct. Is there any good way in terms of effectiveness? Oh, sorry.
I understood. I can repeat the question. Was that the question? Do you have more to add, or I can repeat the question for you if you want?
Okay. So my question is regarding control domain VM. So I guess it's important to statically assign one physical CPU for it regarding real-timeness. But on the other hand, it could be overkill for its workload. So is there any good way for regarding effectiveness?
Yeah, no, it's exactly like you said. It's exactly like you said. So it can overkill to assign one entire physical core. On the other hand, if you really want to have any guarantees that the control domain will run, to give you an idea, the scheduler of Zen has a regular slot of 10 milliseconds. So this is very non-real time, right? So if you want to have any real-timeness to the control domain, definitely you should disable the scheduling, like use a null scheduler. On the other hand, if you are okay to tolerate like delays of 10, 20 milliseconds, maybe 50 milliseconds top, then it's okay. It really depends on what is your requirement on responsiveness of the control domain. And this is true for all of the safe VMs. So I expect that most people will actually disable the scheduler for the safe VMs, because they're going to want to make sure they always are responsive, not just for real time, but just even for safety. So in general, the recommendation will be to disable the scheduler for the safe VMs, and the control domain definitely is a safe VM. So.
Okay, thank you very much.
Yeah.
I noticed you have AGL listed. Can you comment on any of the other major safety OSs like QNX or Android Auto?
So Android, let me tell you that Zen is not only, or like I repeated several times on the during the talk, the goal of Zen, and maybe one of the unique part of being a type 1 is, in a way, we don't really care about the OS that you run on top. We're trying to support as many as possible and not to make preferences. And of course, we work more closely with some than others, like Zephyr and Kate. This is a common combination that we see. Linux, of course. But so QNX, as far as I know, it does run on Zen. Android Auto is something that definitely we run often. In fact, it's even on my IVI slide, I believe. Yeah. So this is something that AMD tests. Like we regularly have it tested. Daily. Yeah. Any other questions? Well, thank you for attending my presentation. And if you have any other question, reach out to me by email or in person while I'm here.